In this video, we're going to solve an example problem using a series solution about an ordinary point. So we've got this second order differential equation, and we're asked to show that x naught equals 0 is an ordinary point of the differential equation. And then we're asked to construct the general solution from two linearly independent series solutions centered at x equals 0. Then we're told that in each case, we want to compute the first 5 non-zero terms of the series solutions and indicate the interval on which the general solution is guaranteed to converge. Okay, so that's the plan. First, we will show that x naught equals 0 is an ordinary point of the differential equation. It's actually really easy. An ordinary point of a differential equation is any x value for which the coefficient functions are well defined and that leading coefficient is not equal to 0. So x equals 0 is in the domain of x plus 1, y equals -2, and y equals 2x. So all three of those functions are well defined. And if this is p of x, that's my leading coefficient. If I plug in 0 to that, I don't get 0. So that means that x naught equals 0 is an ordinary point. So let's state that. We're going to show that p of x naught, which in this case is p of 0, is not equal to 0. That implies that x naught equals 0 is an ordinary point. This is almost too easy to show in a differential equations video, but for completeness, I will show my work. So we're evaluating p of x at 0. 0 plus 1 is 1, and that's clearly non-zero. So x naught equals 0 is an ordinary point of the differential equation. Okay, now we want to construct the general solution. So we will start by assuming that y equals the sum as n goes from 0 to infinity of a sub n times x to the n is a solution of the differential equation. Now, if we expand this, when n equals 0, we'll have a sub 0 times x to the 0. When n equals 1, we'll get a sub 1 times x to the first. When n equals 2, we'll have a sub 2 times x squared. When n equals 3, we'll have a sub 3 times x cubed, then a sub 4 times x to the fourth, and so on. Notice that this subscript and the exponent match, so a sub n is the coefficient of x to the n, or if n is equal to 3, we'll have a sub 3, that's the coefficient of x to the third. And now we're just trying to find the values of a sub 0, a sub 1, a sub 2, a sub 3, and so on, so that this series satisfies this differential equation. So this is the form of our solution. And since this is the form of the solution, then the only unknowns here, are a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, and so on. We want to substitute this into the differential equation and find out what those coefficients would have to be so that this infinite series satisfies that differential equation. So in order to do that, we need the second derivative and the first derivative of this infinite series. Now, if I were computing y prime term by term, the derivative of this term would be 0. The derivative of a constant times x would just be the constant. Here I've got a constant times x squared, so I'd bring the constant down, and then I multiply by the derivative of x squared. So I have 2 times x to the 1 less power, that's just x to the first. Then I'll bring this constant down, and then I'll say what's the derivative of x cubed, bring the power down, multiply by x to the 1 less power, bring the constant down, bring the power down, multiply by x to the 1 less power, and so on. But we'd like to do that in a shorthand way. So rather than doing this, we're just going to take the derivative of every single term at the same time by taking the derivative of the expression that looks like that. Now, this is the derivative of this sum. And remember, you are taking the derivative with respect to x. Now, it looks like n is a variable. It's not. N is just a counter, and it tells you which term you're on. The variable here is x, so we're differentiating with respect to x. And we've got a sum of infinitely many terms. It looks like an infinitely long polynomial, and we're taking the derivative of that sum. Well, from Calculus 1, we know that the derivative of the sum is the sum of the derivatives. So you can pull that derivative operator inside, which is just what we did up here when we took the derivative of that piece and then added the derivative of that piece and added the derivative of that piece. When we took the derivative of each of those terms separately and then added them together, what we were doing was this. We're taking the sum as n goes from 0 to infinity, and then we're taking the derivative of each of those terms separately. Well, a sub n is a constant, so we could bring that down or bring that out of that derivative operator, and then we would just focus on that x to the n. Well, the derivative of x to the n is n times x to the n minus 1, because we bring the power down, we multiply by x to the 1 less power. But notice that when n equals 0, we get 0. If I plug in n equals 0 to this, I get a sub 0 times x to the 0 minus 1. But that factor of 0 zeroes the whole thing out, and we have that 0 there. So rather than starting our counter, our index at n equals 0, because we don't want to count this first term, we'd like to start counting with that first non-zero term. Let's start our counter at n equals 1. Then when n equals 1, we'll have a sub 1 times x to the 1 minus 1. 1 minus 1 is 0, x to the 0 is 1. So this is a sub 1 times 1, or just a sub 1. So if we start with n equals 1, that's giving us our first non-zero term. Now, I'm only going to show you this a couple of times. I'll show you while I'm doing this example, but in future examples, we're going to take this for granted, and we're just going to say if y equals this, then the derivative of y is equal to this. But this comes from this. This is why we start our counter at n equals 1, and why this expression looks that way. So we computed y prime, and now because we have a second order differential equation that we're attempting to solve, this guy right here, we want to compute y double prime next. Now, if I'm taking the derivative term by term again, I would get the derivative of 0, which is 0, plus the derivative of a constant, which is 0, plus the derivative of a constant times x, which is just the constant. Here, I've got a constant times the derivative of x squared. So I'd bring my power down, multiply by x to the 1 less power. Here, I've got a constant times x cubed, so I bring my power down, and I multiply by, or I bring the constant down, then I multiply by the derivative of x cubed. So I bring the power down and I multiply by x to the 1 less power again, and so on. And of course we could simplify that. But again, we want that shorthand notation for this. So if I'm taking the derivative of y prime in order to get y double prime, I'm taking the derivative of an expression that looks like that. So this is a derivative of an infinite sum. From Calculus 1, the derivative of the sum is a sum of the derivatives, so you can pull that derivative operator inside, just like we're taking the derivative term by term and then adding them together, just like we did that here. Remember, your variable is x. N is just a constant for a particular term. When n is 2, this is going to be a sub 2 times 2 times x to the 2 minus 1, or x to the first. Well, yeah, that's that term right there. And then we're going to take the derivative of that to get this guy. Okay, so the derivative of the sum is the sum of the derivatives. And when I'm differentiating, I'm remembering that n is a constant and a sub n is a constant for a particular term. So I bring my constant a sub n down, I bring my constant n down, and then I just focus on that x to the n minus 1. The derivative of x to some power is that power times x to the 1 less power. But notice that when n equals 1, I get a 0 here because 1 minus 1 is 0. When n equals 1, I get this term, that 0, which was the derivative of that a sub 1. So I don't want to start counting at n equals 1 because then I'd be adding that 0 at the beginning, and I prefer not to add that 0 at the beginning. Instead, I want to start counting here, or start counting at the first non-zero term. When n equals 0, we get 0. When n equals 1, we get 0. But when n equals 2, we'll have 2 times, or we'll have a sub 2 times 2 minus 1. That's 2 times a sub 2 times x to the 0, which is 1. So that's our first non-zero term. So we increase that counter from 1 to 2, just so that we're not starting to count with those zeros at the very beginning. Okay, so we've got our y prime, our y double prime, and our original formed for y, and we're going to substitute those into the differential equation. Now the differential equation was given this way. If you have a binomial or a trinomial times a derivative, as we do with that first term, that first expression there, what I recommend is that you distribute that derivative through the parentheses. So we'll have x times y double prime plus y double prime minus 2 times y prime plus 2x times y equals 0. And we're going to substitute in y double prime here and here. We'll substitute in y prime here, and we'll substitute in y there. And then we're going to set all of that equal to 0. And after we substitute, we always want to simplify. Okay. So x times y double prime is x times the sum as n goes from 2 to infinity of a sub n times n minus 1 times x to the n minus 2. And then I've just got y double prime, which is that expression there. So I'll just write it down again. And then we're subtracting 2 times y prime. That was the sum as n goes from 1 to infinity of a sub n times x to the n minus 1. And then we're adding 2x times y, which was the sum as n goes from 0 to infinity of a sub n times x to the n. And all of that has to equal 0. Okay, so from here we want to simplify. But remember, you want to think of this as an infinitely long polynomial. Let's say you've got x times an infinite series that looks like this. Well, if I was taking an infinite series and I was just multiplying it by x, all I would do is distribute that x to every term. So that would give me an x plus x squared plus x cubed over 2 plus x to the 4th over 3 plus x to the 5th over 4, and so on. But that is exactly the same thing as increasing the power of x here by 1. So there was an x to the 0 here. Now there's an x to the first. That was an x to the first. Now it's an x squared. That was an x squared. Now it's an x cubed. That was an x cubed. Now that's an x to the fourth. Now we've got an x to the fourth, and we multiply by an x, and it's x to the fifth. So we're just increasing that power of x by 1, which is exactly what we want to do right here. So when we distribute that x to that entire infinite series, what we get is this. You have the sum as n goes from 2 to infinity of a sub n times n minus 1 times x to the n minus 2 times x to the first. Remember from algebra, you add the exponents, so that's going to give us an x to the n minus 1. This guy, there's nothing to distribute, so I'll just rewrite it. We're just simplifying here. I'll distribute my -2 into that series. And here I want to distribute the 2 and I want to distribute the x. So I've got 2 times all of this. Well, the way we would do that is we would take the 2x and multiply every single term by that 2x, right? Well, that's the same as pulling that 2x inside this summation. So I'll have 2 times a sub n as my constant. And then I'll have x to the first times x to the n, which is going to give me an x to the n plus 1. And that's equal to 0. Now, in order to find the solution to this differential equation, we want to write the left-hand side as a single infinite series, and then we want to think of the right-hand side as an infinite series with infinitely many 0 terms. So you're going to have 0 plus 0x plus 0x squared plus 0x cubed, and so on. But in order to do that, first I need to write this side as a single infinite series. Now, I have to think about how we would do that. I think it's easier to see if we have it in expanded form like this. Let's say you've got this series. And then you're adding it to this series. And then you keep going. Whoops. Okay. Well, if I wanted to add these, I would add them in the same way that I add polynomials. I would add them term by term. But if there are any terms that don't have a like term up here, I would just write those terms down first. So first I would collect the constant terms, but there's only one constant term, it's a 1, so I would just write that down. And then I would collect the x terms. Well, there's only one x term, so that's an x, and I would just write that down. But then once I start looking at the x squared terms, I see I've got 1 over here and 1 over here. Well, then I'd have to add like terms. Well, if I've got half of an x squared and I'm subtracting 2 x squareds, that's going to give me -3 over 2 times x squared. And I would do the same thing for the x cubed terms. If I've got 1 of these and then I'm adding a third, that means I'm adding 4/3 of those. If I've got 1 of these and I'm subtracting, or 1/4 of an x to the fourth, and I'm subtracting 1 of them, that's going to give me a -3/4 times x to the fourth. And we keep going. So what we had to do in order to add these two series together was we had to take out terms that were just by themselves, where there were no other like terms up there. So we took the 1 and the x and we just wrote them down. So those are here. And then when we had like terms, we had to combine them. We took this x squared and we added it to an x squared to get this. We took the x cubed term and added that x cubed to get this. We took the x to the fourth term and the x to the fourth term, and we got that. And over here, if there's an x to the fifth, I would add it to that x to the fifth term, and we would do that for infinitely many terms. So these guys came from collecting the like terms from this series and this series. But in order to do that, I had to get rid of these guys, these extra terms, this constant term and the x term, that was not available as a like term over here. This series had a constant term and a next term, whereas this one didn't. So I just wrote those down. And then when I was able to collect like terms, I started collecting like terms. Okay, that's exactly what we're going to do here. It's going to look a little different because we're using the summation notation, but it's exactly the same thing. So I want to write this as a single infinite series. In order to do that, I need to do two things. I need to remove terms from series as necessary so that all of the series start with the same power of x. And then once I've removed terms, I want to collect like terms, and that will require writing the series so that they look exactly the same. And when they have exactly the same form, I'll be able to add them together. I know that that was a little bit cryptic, but we will get to the details of how to do that in just a moment. So let's start with our first step because we're going to add these series together in 2 steps. In order to add the series, the first thing we need to do is we need to remove terms from some series. So I'll say from select series, so that all series, all 4 of these guys, start with the same power of x. Now, in order to know which terms or which series I need to remove terms from, I need to think about what types of terms each of these series start with. In order to do that, I just plug in n equals 2 here, and n equals 2 there, and n equals 1 here, and n equals 0 there to find out which term we start with. So when n equals 2, we're going to have x to the 2 minus 1. So that's x to the first. So this starts with an x to the first term. When n equals 2 here, I've got a constant times x to the 2 minus 2, or x to the 0. So this starts with a constant term. And I'll call it an x to the 0 term. It's just another name for a constant term. When n equals 1, I have x to the 1 minus 1. So it's another x to the 0. So this starts with a constant term, or an x to the 0 term. And then here, when n equals 0, I have an x to the 0 plus 1, which is an x to the first. Now remember how this works. We want to remove terms from some series so that all series start with the same power of x when we're done. Remember how we did that over here when we're making it a little bit more concrete for ourselves. We had to, in order to combine these two, we had to remove terms from this series, the one that started with the constant term and the x to the first term, so that the remaining series started with an x squared. So that way this one started with an x squared and this one started with an x squared, and we were able to add like terms. So you're going to have to remove terms from this series that starts with the lower degree terms. So I have to take out the constant term and the x term so that what remains is an x squared term and then higher order terms. And the same is true over here. But we didn't have to take out any over here because this one didn't have a constant term or an x term. Okay, going back to this. So when I'm looking at these and I'm trying to decide which series I'm going to remove terms from, I'm looking for the one that starts with the lowest power of x. And then I'm looking also at the ones that have the highest power of x. So these both start with an x to the first term. In order to make this one also start with an x to the first term, and to make this one start with an x to the first term, I've got to remove the constant term from this one and the constant term from that one. Then all 4 of these will start with an x to the first term. So this is the plan in general. For this specific example, we're going to remove the x to the 0 term from the second and third series so that all series start with an x to the first term. So we're just going to take a term out, and then the series that's left will start with an x to the first. Okay, so let's do that. So this first term already starts with an x to the first, or this first series does. So we're going to leave it alone. And this one starts with an x to the 0 term. Now when n equals 2, we get x equals, or x to the 0 here. So what I'm doing is I'm taking out the n equals 2 term. I'm saying instead of starting and adding that whole series, we're going to say, let's remove the n equals 2 term, which is a sub 2 times 2 minus 1, which is 1, times x to the 2 minus 2, which is x to the 0. So that's our constant term. And then the rest of the series is going to look exactly the same, but you're going to pick up where you left off. That's the n equals 2 term. The rest of the series starts with n equals 3. So these two together give you that second series. So this was our first series. We didn't do anything to it. Our second series was this constant term plus this series. And now this one starts with an x to the 0. So the third series needs to have a term removed from it as well. Now in this one, the first term of the series is indexed by this n equal to 1. So I will evaluate this expression at n equals 1, and I'll get the constant term from that. So I'll have negative 2 times a sub 1 times n, which is 1, times x to the 1 minus 1, or x to the 0, which is 1. So that's our n equals 1 term, and then the rest of the series looks exactly the same. But we pick up where we left off. If this is the n equals 1 term, the next term, or the rest of the series, starts with n equals 2. So these two pieces together give us the third series from this list of 4 series. And that last one already starts with an x to the first term, so we're just going to write it down. And this series plus this series plus this series plus this series is equal to 0. Okay, so now we've got some constants outside, and then we've got 4 infinite series that all start with an x to the first term, but they don't look the same. The next part, the next necessary step, is to make them look the same so that it's obvious what the relationship is between the coefficients. So when n equals 2 here, we get an x to the 2 minus 1. That's going to be an x to the first. When n equals 3 here, we have an x to the 3 minus 2, which is also an x to the first. When n equals 2 here, you've got x to the 2 minus 1, which is an x to the first. When n equals 0, we get an x to the first as well. So they all start with the x to the first, but I can't just add this to this because the n represents something different here. I want them all to look the same, so I can just add the coefficient of this guy to this guy and to this guy and to this guy, so that I know the coefficient of x to some power, just like I did over here. When I wanted to add this x squared term to this x squared term, I had to identify the x squared terms, and then I had to add the 1/2 and the -2 to get the -3/2. That's exactly what we want down here. That's exactly the plan. But we have to make them look the same in order to do that. So we've removed terms from the series so that they all start with the same power of x. The next part of this requires us to relabel the terms. So we're relabeling the series so that all series look the same. So I'm going to say identical. Basically, we want the exponents to look the same. We want the exponents to be identical. So I'm focused on this exponent, this exponent, this exponent, and this exponent, and I want them all to look the same. I want to have the exact same pattern. Now, both of these are n minus 1. This is n minus 2, and that's n plus 1. So it would be the least amount of work to change both of these to look like these. We'll leave these guys alone, and we'll just make this exponent look like this exponent. And we'll make this exponent look like these exponents. And then they will all look the same, and we'll be able to add like terms in much the same way that we did on that other page. Okay, so in order to relabel the series, this is what you'll do. You're going to take the exponent you have, n minus 2 in this case, and you're going to let it equal the exponent you want. Now, we can't say that n minus 2 is equal to n minus 1. That's nonsense. But we want them to have the same form as n minus 1. So rather than using an m, we're going to replace that with a k. I'm going to say that we want to let n minus 2 here equal k minus 1. And then we'll solve for n by adding 2 to both sides. And then we'll solve for k by subtracting 1 from both sides. And then we can write this series entirely in terms of k. And on this one, I'm going to want the exponent to look like this exponent, which is going to be a k minus 1 later. So I'll just let n equal k over here. And on this one, I will let n equal k as well. And then we'll make a substitution for that one. But I'll do that when we get there. Okay, so let's collect the constant terms first. You've got 2a sub 2 minus 2a sub 1. So those are our constant terms. And then over here, we're going to add that first series. But we're going to replace all the n's with k's. So we're going to write that as the sum as k goes from 2 to infinity of a sub k times k minus 1 times x to the k minus 1. Okay, and we already took care of that constant. And now this one is the one that we have chosen to relabel. Again, we set the exponent we have equal to the exponent we want. But for the exponent we want, we replace the n with a k. So we set n minus 2 equal to k minus 1. And then we solve those equations for both n and k. And now we want to write this second series in terms of k rather than n. This is our first series. Now we're working on our second series. So for our second series, we start with n equals 3. But we want to write this in terms of k rather than n. To find the k value where we start, we plug in n equals 3 to this equation. When n is equal to 3, k is equal to 3 minus 1, which is 2. Okay. And then over here, every time you see an n, you're going to replace it with a k plus 1. This is a sub k plus 1 times n, which is k plus 1, times n minus 1, so that's k plus 1 minus 1, which is just a k, times x to the k minus 1 by design. And if you're not sure, you can replace n with k plus 1. K plus 1 minus 2 is k minus 1. Okay, so that's our second series. Now the third series, we're going to pretty much leave alone. You're just replacing the n's with k's. So we'll have the sum as k goes from 2 to infinity of negative 2 a sub k times x to the k minus 1. And then for our fourth series, it doesn't look like that k minus 1 that we want it to look like. So we're going to take the exponent we have, oops, it's k plus 1. We're going to set it equal to the exponent we want, but we'll replace the n with a k. So we want n plus 1 to equal k minus 1, solve for n by subtracting 1 from both sides, and then solve for k. So n is equal to k minus 2, and k is equal to n plus 2. And now we want to write this series entirely in terms of k. This is our fourth and final series. When n equals 0, k is 0 plus 2. So k starts with 2. Then we have 2 times a sub n, and n is replaced by k minus 2. And then this is an x to the n plus 1, which is equal to k minus 1. All right. Now we are just relabeling this series. And if you're saying to yourself, I'm not so sure that this is actually equal to that after that relabeling, you should check it out. Plug in k equals 2. What do you get? A sub 2 times 2 minus 1 times x to the first. So you're going to end up with 2a sub 2 times x to the first. See what you get when you plug in n equals 3 to this one. Oh, that was the first series, sorry. For the second series, if we plug in k equals 2 to this, we get a sub 3 times 2 plus 1 is 3 times 2. So we have a sub 3 times 2 times x to the first. Over here, if n is equal to 3, I'm sorry, the first time I was looking at the first series and the second series, and I misaligned them. I need to show that the second series here is equal to the second series here. When n equals 3 here, I have 3 times 3 minus 1, so that's 3 times 2, times a sub 3 times x to the first. When k equals 2, I have a sub 3 times 2 times x to the first. So it's the same thing, we've just shifted the indices. So we're writing that expression, we're writing that series in a different form. And the reason we did that is now we'll be able to add like terms. So I've got this times x to the k minus 1, and this times x to the k minus 1, and this times x to the k minus 1, and this times x to the k minus 1. So now since they all look the same, we can write them in one summation. Notice also that after relabeling the indices, all 4 series start with k equals 2. So we're going to start counting at k equals 2. And when k equals 2, we're going to have an x to the first for all of these guys, and then we'll just add the like terms here. So now that we have relabeled our indices, we can add like terms. We can write these 4 series together as a single series. So we have 2 times a sub 2 minus 2 times a sub 1 plus the sum as k goes from 2 to infinity of these guys. Now I'm factoring out the x to the k minus 1. So I have a sub k times k minus 1, or times k minus 1, times x to the k minus 1, plus a sub k plus 1 times k plus 1, minus 2 times k times a sub k, plus 2 times a sub k minus 2, all of that times x to the k minus 1 is equal to 0. So the whole point of all of that, removing terms so that they all started with the same power of x, and then relabeling them so that the exponents match. The reason we did that was so that we could add all 4 of those series together as this single series. So I've got a constant plus a constant times x to the first, plus a different constant times x squared, plus a different constant times x cubed. And that's equal to this 0 over here. Now this 0 we can think of as a sum of infinitely many zeros. Well, it doesn't really matter where we start our index, but you could start with k equals 1 if you wanted to. So we'll have 0 plus 0x plus 0x squared plus 0x cubed, and so on. Now, the only way that this infinite series on this side is equal to this infinite series on this side is if the coefficients are equal. Because the powers of x are linearly independent from each other, that's the only way that this can possibly hold. So when you realize that this is an infinite series and that 0 over there can be thought of as an infinite series of infinitely many zeros, then you can find a relationship between these a sub k's and a sub k plus 1 and a sub k minus 2 and all of that using this equation and this equation. So the only way these guys are equal is if the coefficients are equal. Coefficients of x to the n are equal. So we'll set the constant term on this side, which is this 2a sub 2 minus 2a sub 1, equal to the constant term on that side, which is 0. And we'll set the coefficients of x to the k minus 1 equal to 0. And I think I'd like to simplify that. So I have a sub k. Here I've got, if I distribute, k squared minus k minus 2k. So these guys have been combined, plus a sub k plus 1 times this expression, which I think I'll leave factored. That's k times k plus 1, plus 2 times a sub k minus 2. That is equal to 0 for k equals 2, 3, 4, and so on. This is going to allow us to find the coefficients a sub k. Now at this point, after you've set the coefficients on the left-hand side equal to the corresponding coefficients on the right-hand side, we want to take each of these equations and solve for the coefficient with the largest subscript. So I want a sub 2 here in terms of a sub 1 because 2 is larger than 1. And down here, I'm going to solve for the coefficient with the largest subscript as well. I'm comparing the k plus 1, and the k minus 2. Well, k plus 1 is the largest, so I'm going to get that guy by itself. Now on this one, it's pretty easy. If you just add the 2 times a sub 1 to both sides and then divide by 2, you get a sub 2 is equal to a sub 1. And then this one is going to take a little bit more algebraic manipulation. So I will do that on the next page. So we have set the coefficient of x to the n on the left-hand side equal to the coefficient of x to the n on the right-hand side, using LHS as an abbreviation for left-hand side and RHS as an abbreviation for right-hand side. And then, of course, on the right-hand side, that was just infinitely many zeros. So we're really setting the coefficients of x to different powers equal to 0. And then once we do that, we are solving for the coefficient with the largest subscript. And the reason we're doing that is because when we do, we can sort of build up our list of subscripts. We can get a sub 2 in terms of a sub 1 and a sub 0. And then once we've got a sub 2 in terms of a sub 1 and a sub 0, we can get a sub 3 in terms of a sub 2 and maybe a sub 1. But since a sub 2 is written in terms of a sub 1 and a sub 0, we'll be able to get a sub 3 in terms of a sub 1 and a sub 0. Then once we have that, we can get a sub 4 in terms of a sub 1 and a sub 0. So if we solve for the coefficient with the largest subscript, we're going to be able to get all the coefficients if we wanted to in terms of a couple of the other coefficients. And usually those coefficients are the a sub 1 and a sub 0. Although sometimes it's two different ones because maybe one of those is 0. Okay, so that's the plan. From that last line, we had a sub 2 is equal to a sub 1. And now I'm here, and I'm trying to get this guy by itself. So I'm going to subtract this from both sides and subtract that from both sides, and I'll simplify that one as well. So we'll have a sub k plus 1 is equal to negative a sub k times k squared minus 3k. That's the simplified version of this. And then I'm subtracting this from both sides as well. So I'll have minus 2 times a sub k minus 2. And then I've got, that will be equal to this, but I want the a sub k plus 1 by itself. So I'll divide both sides by the k times k plus 1. And this is true for k starting at 2, because that's the value of the index where we start counting for this infinite series. Now, if you chose different ones to match to, and for example, many times everyone will make, or some teachers will make all series look like an x to the n so that they can be added together. Well, then your counter would start at a different place, but it would still represent, well, the first non-zero term here involves an x to the first. So it would be the same thing in slightly different form. But if you plugged in the values of that index, you would get exactly the same series. Okay, so this is telling us where to start. We're going to start with k equals 2. All right. So in k equals 2, this is a sub 3. We have that equal to negative k, or a sub 2 times 2 squared minus 3 times 2. So that's 4 minus 6, which is negative 2. And then when k equals 2, this is a sub 2 minus 2, which is a sub 0, all divided by 2 times 3. K is 2, and 2 plus 1 is 3. So we end up with a negative 2 times a sub 2 over 6, or a positive 1/3 times a sub 2 there. And then over here, the 2's are going to reduce, and we'll have minus 1/3 times a sub 0. But we already know that a sub 2 is equal to a sub 1 from that earlier equation. So a sub 3 can be written in terms of a sub 0 and a sub 1 this way. A sub 2 is the same as a sub 1 from earlier, so we have this. Okay, now let's see what we get when k equals 3. Then we'll have a sub 4 equals negative a sub 3 times 9 minus 9 is going to be 0. Minus 2 times a sub 3 minus 2, which is 1, all divided by 3 times 4. So this guy is gone. That term is gone because it's 0. And then over here, I've got negative 2 over 12, which is negative 1/6 times a sub 1. And we'll keep going. When k equals 4, this is a sub 5 equals negative a sub 4 times 16 minus 12, which is 4, minus 2 times a sub 4 minus 2 is 2, all divided by 4 times 5. So this will become a negative 1/5 a sub 4 minus 2 over 20, which is minus 1/10 times a sub 2. And a sub 4 is negative 1/6 of a sub 1. And a sub 2 was equal to a sub 1 from earlier. Oops, I'm sorry, I'm off the screen. A sub 2 was a sub 1 from earlier. So we end up with 1 over 30 times a sub 1 minus 3 over 30 times a sub 1. So that's going to be negative 2 over 30, or negative 1/15 times a sub 1. Okay. Now let's evaluate this at k equals 5. So I have a sub 6 equals negative a sub 5 times k squared, which is 25, minus 3 times 5, which is 15, minus 2 times a sub 5 minus 2, which is 3, all divided by 5 times 6. So we end up with negative 10 times a sub 5 over 30 minus 2 over 30 times a sub 3. So this is negative 1/3 times a sub 5 minus 1/5, or excuse me, 1/15 of a sub 3. And a sub 5 ended up being negative 1 over 15 times a sub 1. And a sub 3 is 1/3 of a sub 1 minus 1/3 of a sub 0. Now, if you're wondering to yourself, when do we get to stop? I'll get to that in just a moment. Let's simplify this. This is a negative 1/15. So it's going to be a positive 1 over 45 times a sub 1 minus 1 over 45 times a sub 1 plus 1 over 45 times a sub 0. And these guys happen to reduce. And so we get this. Now, if you're saying, how do I know when to stop? That's an excellent question. Now remember, we were looking for two linearly independent series solutions of the differential equation. It's kind of hard to remember, but way back when we said that y is going to look like this. It's a constant plus a constant times x plus a constant times x squared plus a constant times x cubed and so on. And notice, because of that recursive relationship between the different subscripts, we're able to get a sub 2, a sub 3, a sub 4, and so on, all in terms of a sub 0 and a sub 1. That's not an accident. That's going to lead to the two linearly independent infinite series. So what we are going to want in order to get the first 5 non-zero terms of the two linearly independent series solutions to the differential equation, the two that are centered at 0, what we're going to want are 5 terms that involve this a sub 0 and 5 terms that involve the a sub 1. Now we automatically get the first a sub 0 term and the second, or in the first a sub 1 term, but we need 4 more that depend on a sub 0 in order to have 5 non-zero terms in that first series. And then we need 4 more terms that depend on a sub 1 in order to have 5 non-zero terms for the second series. Okay, so got one term for a sub 0. And then you've got another term, so that's 2. And then we've got another term, so that's 3. So we've got 3 terms that involve a sub 0 so far. So we need 2 more terms that involve a sub 0. And we want a total of 5 terms that involve a sub 1 as well. So we had that first one that depended on a sub 1, just the automatic one. Then we've got a second one, and a third one, and a fourth one. And we actually have a 5th one right there. So we already have enough terms for the a sub 1, but we still need 2 more that depend on a sub 0 because we only have 3 so far. So we need to keep going. So we found this coefficient, a sub 6, by substituting k equals 5. Now we're going to substitute k equals 6. So we'll have a sub 7 equals negative a sub 6 times 6 squared, which is 36, minus 3 times 6, which is 18, minus 2 times a sub 6 minus 2, which is 4, all divided by 6 times 7. So this is going to give me a negative 18, which is 6 times 3, over 6 times 7 times a sub 6. And then I'll have minus 2 over 6 times 7, or minus 1 over 3 times 7 times a sub 4. The 6's reduce. And so we'll have negative 3 over 7 times a sub 6, and a sub 6 simplified to 1 over 45 times a sub 0. And then here I've got minus 1 over 21 times a sub 4, and a sub 4 was negative 1 over 6 times a sub 1. So these guys will simplify a little bit further. 3 goes into 45 15 times. So this is going to be negative 1 over 70 plus 35, 105, times a sub 0, plus 1 over 20 plus, or 120 plus 6 is 126 times a sub 1. Okay, so now we've got 4 coefficients in terms of a sub 0. We need one more. So that was k equals 6. Now we want k equals 7. And the formula was a sub k plus 1. So we'll have a sub 8 here equals negative a sub k, which is 7, times 7 squared, which is 49, minus 3 times k, which is 7. So minus 3 times 7, which is 21, minus 2 times a sub k minus 2. If k is 7, we're going to have 7 minus 2, which is 5, all over k times k plus 1, so 7 times 8. So this becomes negative 28, which is negative 7 times 4 times a sub 7 over 7 times 8, minus 2 over 7 times 8, which is the same as negative 1 over 7 times 4 times a sub 5. These guys reduce, and of course the 4 over 8 reduces to a negative 1/2. And then I want to substitute in a sub 7. Now a sub 7 from the last page was this. That's negative 105 times a naught. Negative 1 over 105 times a naught, plus 1 over 126 times a sub 1. Yep, that's right. And then I've got a negative 1 over 28 times a sub 5. And a sub 5 was negative 1/15 of a sub 1. Okay. So I get 1 over 210 times a sub 0 minus 1 over, what's that, 252 times a sub 1 plus 1 over 28 times 15, which is 1 over 420 times a sub 1. And then I want to add these two fractions together. Now, I don't know what that is off the top of my head. I think I'll use a calculator for that because we don't want to spend too much time in differential equations practicing arithmetic, although it's good to know how to do arithmetic. So we've got 1 over 420 minus 1 over 252, close parentheses, and we get negative 1 over 630. That's times a sub 1. Okay, plus more terms, more coefficients, as many as we want. Now we wanted 5 terms that depended on a sub 0 and 5 that depended on a sub 1, because I told you that that was going to lead to 2 linearly independent series solutions. If you're saying, how does that work? I'm going to show you now. So you've got a sub 1 or a sub 0 through a sub 8, and you want to substitute those into the form of that infinite series that we started with. So you've got a sub n times x to the n, so that's a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x cubed, and we're going all the way out to a sub 8, so we want to go all the way up to x to the 8th. So I'll have x to the 4th times a sub 4 plus a sub 5 times x to the 5th plus a sub 6 times x to the 6th plus a sub 7 times x to the 7th plus a sub 8 times x to the 8th plus a sub 9 times x to the 9th plus a sub 10 times x to the 10th plus a sub 11 times x to the 11th, and you could just keep going. Okay. Now we want to substitute in all the values for a sub 2, a sub 3, and a sub 4 that we found in terms of a sub 0 and a sub 1. So we're going to leave these first two terms alone. And then we'll substitute in whatever we had for a sub 2. Well, a sub 2 is equal to a sub 1. So I'm replacing this with a sub 1. And then a sub 3 turned out to be this expression, 1/3 of a sub 1 minus 1/3 of a sub 0. That's a sub 3, and we're multiplying a sub 3 by x cubed. Okay, then we want a sub 4. A sub 4 was negative 1/6 of a sub 1. That's multiplied by x to the 4th. Then we want a sub 5, which is negative 1/15 of a sub 1. Okay. Now we want the coefficient of x to the 6th, which is a sub 6. And a sub 6 was 1/45 times a sub 0. Guess I left more space than was necessary there. It's okay. Then I want the coefficient of x to the 7th, which is this negative 1/105 times a sub 0 plus 1/126 times a sub 1. Okay. And then we want the coefficient of x to the 8th. Which is this 1/210 times a sub 0 minus 1/630 times a sub 1. Plus the x to the 9th term, the x to the 10th term, the x to the 11th term, all the way on to infinity. Okay, now we were asked to find two linearly independent series solutions. I claim that they're in here. You've already labeled them, or you've already got them. They're just not written in the right form yet. In order to find those two linearly independent solutions, you're going to collect terms that involve a factor of a sub 0. So I'm going to underline those terms. I've got an a sub 0 term here. That's the first one. And then I've got a second a sub 0 term there. There's my third a sub 0 term. And then there's my fourth a sub 0 term. And then there's my fifth a sub 0 term. Now remember, we were asked to find the first 5 non-zero terms of each of those series solutions. So I found 5 terms that involve an a sub 0. So I'm going to look at those 5 terms and I'll factor out the a sub 0 from those. And I say, well, a sub 0 times what gives me the first term? Well, it's just a 1. And then here I'll have a negative 1/3 times x cubed times a sub 0. And here I've got a 1/45 times x to the 6th times a sub 0. And here I've got a negative 1/105 times a sub 0 times x to the 7th. And then here I've got a 1/210 times a sub 0 times x to the 8th, plus higher order terms. Okay, so that's that. And now I also want the x to the, or the terms that involve a sub 1. So I've got a term that involves a sub 1 here, and another one there, and then another one there, and then one there, and one there, and one there, and one there. So I've got more than the 5 that I need on this one. That's okay. Got at least 5, which is what we wanted. So a sub 1 times x is that first one. Then I've got a sub 1 times x squared is the second one. And I've got 1/3 a sub 1 times x cubed. So I've got a 1/3 x cubed times a sub 1 there. Negative 1/6 x to the 4th. Then I have minus 1/15 times x to the 5th. And I could stop there because I was supposed to find 5 non-zero terms involving a sub 1. But since I found the other 2, I think I'll add those on as well. So then I've got 1/126 times a sub 1 times x to the 7th plus, or actually minus, this 1/630 times x to the 8th plus higher order terms. Now that is our general solution. because we've got a constant times the first function, or a constant times the first infinite series solution centered at 0, plus a constant times the second infinite series solution centered at 0 is equal to y. So that's our general solution. So we have y equals a sub 1 times y1 plus a sub 0 times y1 plus a sub 1 times y2. Normally we would call that c1y1 plus c2y2, but it's the same thing, just different labels for the constants. Okay, so I'm just going to go through those steps with you one more time, and then we'll talk about the interval of existence, or in other words, the largest interval where these solutions are guaranteed to converge. So way back here, we said that once we were able to add those series together, the only way the series on the left-hand side was equal to the series on the right-hand side, which is a series of infinitely many zeros, is if the coefficients of x to the n on the left-hand side equal the coefficients of x to the n on the right-hand side, which is just 0. So we took those and we were able to write a couple of equations down. And then we took each of those equations and we solved for the coefficient with the largest subscript so that we could get a sub 2 in terms of a sub 1 and a sub 0. And then we could get a sub 3 in terms of a sub 2 and a sub 1 and a sub 0. But since the a sub 2 was in terms of a sub 1 and a sub 0, we were able to get a sub 3 in terms of a sub 1 and a sub 0. Because of that recursive relationship, as long as we solve for the one with the largest subscript, we can build up our list of coefficients. And all of them can be written in terms of those first two terms, the first two coefficients, a sub 0 and a sub 1. So we did that. And then we evaluated this expression for as many terms as necessary until we got 5 coefficients that depended on a sub 0 and 5 coefficients that depended on a sub 1. So I'll say evaluate the recursive relation for the coefficients until you have 5 coefficients that depend on one constant, in this case a sub 0, and 5 coefficients that depend on the second constant. In this case, that was a sub 1. Now, sometimes you'll find out that a sub 0 or a sub 1 has to be 0. In that case, the coefficients might be written in terms of a sub 0 and a sub 2, or a sub 1 and a sub 2, or something like that. But the idea is you're going to have infinitely many terms, usually, unless one of the series solutions turns out to be a terminating series solution or a polynomial. We're going to have infinitely many terms that depend on, or infinitely many coefficients that depend on 2 of the earlier coefficients in the list. Okay, so we did this. And then after we did that, we substituted into the form of our solution. And then we grouped terms involving a sub 0. So in general, you're going to group terms involving the first constant well, I'm just going to say a sub 0 for our example, and group terms involving a sub 1. And then you're going to factor out a sub 1 and a sub 0 to get the general solution. Okay, so that is the general solution of the differential equation, but we need to state the interval where those series are guaranteed to exist. Requires going back to the differential equation. So remember, our differential equation looked like this. We had x plus 1 times y double prime, minus 2 times y prime plus 2xy is equal to 0. Now, if I take this and I rearrange it so that my coefficient of y double prime is equal to 1, I get this, y double prime minus 2 over x plus 1 times y prime plus 2x over x plus 1 times y equals 0. So I'm just taking this equation and I'm dividing by x plus 1. Now, the interval of existence is related to the interval of existence of the power series representations of this function and this function. If we called this, as we did in the derivation, p of x times y double prime and q of x times y prime and r of x times y. This is q over p and that's r over p. And the question becomes, where does the series representation of this function converge? And I want the infinite series representation of that function that's centered at x naught equals 0, that ordinary point where we are centering these two solutions. Well, it's actually really simple. If you've got a polynomial divided by a polynomial, this polynomial over a polynomial will converge on an interval starting at x naught and then going to that nearest singular point of the differential equation. Or in other words, we're going to have a problem with this function when x is equal to -1. So this function, which we can call q of x over p of x, equals -2 over x plus 1. We'll say that it is analytic, which just means that it has a series solution centered at x equals x naught, which equals 0. It's an analytic function at x equals 0, so it can be represented as an infinite series. And the infinite series representation of this will converge on an interval that looks like this. It's going to converge for all x, satisfying the following inequality. The absolute value of x minus x naught is less than r, where x naught is the center of the series, and in our case, x naught was 0. And r is the distance from x naught, in this case x naught equals 0, to the nearest singular point. Okay, so it's a lot of words to say a very simple thing. When I look at that, I say, okay, that denominator is undefined when x equals -1. So the singular point occurs at -1. The series representation of this rational function is guaranteed to converge on an interval that is at least this large. The interval itself might actually be a little bit larger. It might even be all real numbers. For this one, it turns out to not be all real numbers. But in general, it might even be all real numbers. But this tells us where the series is guaranteed to converge. Okay, so this function has a series representation that's guaranteed to converge for all x satisfying this, where r is the distance between x naught, that's our x naught equals 0 in this case, that was given to us, and the nearest singular point. Now Now it's always a symmetric interval about that center. So if this is R, the interval of existence is going to go from -1 to +1, at least. And it turns out that that can be written as a geometric power series. So it actually turns out to be that's the interval of existence. So for this example, we have the absolute value of x is less than 1, which corresponds to x being on the interval between -1 and 1. So that's where that one converges. Similarly, that this rational function has a series representation that converges on the same interval because we're looking at the distance between 0 and the nearest singular point, which is -1. So that's r equals 1. So we've got the absolute value of x minus 0 is less than 1. So that's the absolute value of x is less than 1, which means that x is between -1 and 1. So this is true for this function, and this is true for that function. Since it's true for both of those functions, it is also true for the two linearly independent series solutions that we found earlier. So the general solution is this, where y1 and y2 converge on the interval from -1 to 1. Now, it's possible that they converge from -infinity to infinity or from -10 to 10. We don't actually know, but we're told that these series solutions are guaranteed to converge at least on the intervals where this function is analytic and this function is analytic with infinite series representation centered at that center point x naught equals 0. So where these are analytic, these solutions are going to converge. Yep. Okay, I think that covers everything. So that is our first example of solving a second order differential equation with a series solution about an ordinary point. I will make another video giving you another example. But this is the first one, so I explained a lot more than I typically would with this first example than I will on the next one. So if you are a person that would like less explanation rather than more, you can just look at the next video rather than this one.